Thank you very much for inviting me to do this talk. Good morning, everyone. I was asked to do this talk to introduce you to physics in healthcare. And I thought, well, that's an easy job, isn't it? And then I started to try and do it. And I realized this is actually quite a difficult job because to do it in 35 minutes, because there is just so much wonderful physics in healthcare. So I started off by thinking, well, what about physics? Where does physics come into healthcare? And this first slide shows you some items which I think you'll all agree are physics, no doubt about it. And I'm sure you've all studied them in your physics degree. And these are just some of the things, some of the physics that comes into medicine. So if we then look at what we do in medicine, well, the first thing we probably do to a patient in medicine is actually to try and make a diagnosis. And how can we do that? Well, X-ray imaging. I'm going to say a little bit more about that in a moment. We then can do computed tomography, which has already been mentioned and is a more advanced way of doing X-ray imaging. We can do ultrasound, which is a very interesting area of physics in medicine. Nuclear medicine, I think, is fascinating, using radioactivity. Magnetic resonance imaging, a very complex way of doing fantastic imaging. And then a couple of other ways which are also physics, but not quite in the same way, endoscopy and pulse oximetry. So those are some major ways of doing diagnosis. And most people who go to hospital will have one or other of those done to them. And then we look at treatment. Well, having decided what's wrong with the patient, we want to be able to help to treat them. And the major way that physics comes in there is radiotherapy. And we can do external beam radiotherapy. We can use X-rays, electrons, charged particles. And then we can do what we call brachytherapy. I'll explain a little bit more later, which involves actually using radioactive sources near the tumor or in the tumor. And we can do something called unsealed source radiotherapy. So there is a lot of physics there and a lot of need for really good physicists to do things. So let's make a start. I'm going to start with, at the beginning, with this guy, Wilhelm Conrad Röntgen, because I think there's a nice story here. And I think he was a really good scientist, this guy, because what he did was he discovered X-rays in 1895. At the time, what he was doing, it was what a lot of other people were doing at that time, which was playing around, doing experiments, if you like, with something called a Crookes tube, which is an evacuated glass tube. And they knew that at that time that if we had a voltage between the two electrodes in the tube, one here and one here, we could get a beam of cathode rays. They didn't know at that time what cathode rays were. It turned out a few years later that they're actually what we now know as electrons. And Röntgen was doing experiments with these, and then he suddenly noticed something rather odd. That when he turned on the voltage in his tube, across the other side of the room, he got a glowing, and it was a container of a material which scintillates, which glows, barium platinum cyanide, which glows when it is hit by some high energy rays. And he thought that's odd, and he turned his Crookes tube off, and the glowing stopped, and he turned it on again, and it started. So he thought there must be something going from one place in my lab, in my Crookes tube, across the other side. It must be some kind of ray. I can't see it. What is it? And of course, you don't know what something is. You call it X, don't you? So he called it X-rays. But the good thing about Röntgen was that he didn't just dismiss it. He didn't say, oh, ignore this. And get on with doing my experiments on my was that he found several things about them. He found they traveled in straight lines. He didn't know what they were. They traveled in straight lines. And he found out they penetrated some materials more than others, and they exposed photographic plates. Now that was quite a breakthrough. So one day he got his wife to come into the lab and got her to put her hand on a photographic plate and exposed it to X-rays. And when he developed the plate, this is what he got. So this is the very first medical image, if you like. He created an image of his wife's hand. And he published this in early 1896, and things really took off. And what we noticed from this Well, what we think about as physicists, we say, well, why do we get an image? Well, we must be getting an image because the X-rays are penetrating the soft tissue. That's the area around here that you can't see at all on this picture. The X-rays are penetrating the soft tissue much more than they're penetrating the bone. And they're penetrating the bone much more than they're penetrating this, which is obviously Frau Röntgen's wedding ring, which is going to be a heavy metal. So he published this and things absolutely took off. Wonderful discovery. It was the first time that anybody had been able to look inside another human without cutting them open. So we now know that X-rays are in fact part of the electromagnetic spectrum. Here they are, the high energy end of the electromagnetic spectrum. And I'm sure you've all done this in your degree courses. As physicists, we have to stop and say, okay, let's ask some physics questions. What are the interactions with tissue? Well, the answer to this turns out to be all sorts of interesting things like the Compton effect and the photoelectric effect and so on. And then we have to say, well, what's the best way to detect X-rays? Röntgen used photographic plates because he happened to discover that it worked that way. Nowadays, we have more sophisticated digital detectors, but we still have to work out what is the best way to actually do this. What energy of X-rays is best? As you can see from here, there's a range of energies. Which is the best energy to use for any particular use? So lots and lots of interesting physics questions there. So I thought I'd just flash up next very quickly an image of a modern X-ray system. We now have digital detectors. The images we get are now pretty much instant. And thanks to a lot of work on things like what energy we use and so on, the radiation dose is a lot lower than it would have been in Röntgen's days. So that's a modern X-ray system. But that's taking a planar X-ray. In other words, just going through from one side of the body to the other. And that's all very well, but it doesn't give you very much information about several things. It doesn't give you any information about depth. You can't tell how far into the patient something is. You can have one thing hidden behind another. These X-rays, as you saw from that very early picture, they're very good at showing bones and metallic objects, but they don't distinguish different types of soft tissue very well at all. So in the 1970s, there was, and you've already seen a slide of the developers of this, Jeffrey Hansfield, the development came along of computed tomography. Why did it take so long to do computed tomography? Well, the main reason is because we needed the computing side of it. It's very complicated trying to work out what you're actually seeing in the image. The mathematics of how to do it was interestingly developed in 1917, but it wasn't until the 1970s that we got computed tomography. And then we could have pictures of slices of patient, and more recently 3D and 4D images. The reconstruction involves quite a lot of maths, for example, Fourier transforms, and a lot of computing. So this is roughly how a CT scanner works. It's a very basic sketch, but this will give you the basic idea, I hope. We have an X-ray source down here, and that produces a fan of X-ray beams, which are detected in a ring of detectors around here. There's sort of at least 1,000 detectors around here these days. And this rotates, both of these rotate together around the patient so that the detectors are opposite the source. And the patient can be moved in and out through this gantry so that you can do the imaging. Now, initially, the initial images were slices like this through the patient. What has now happened is that we now move the patient continuously. We keep this rotating continuously, and we can get much better images. I'm getting an echo back. If somebody can mute themselves, please. Right, modern CT scanners. This is an example of an axial slice through a patient, and I hope you can work out what it is. Even if, like me, as a physicist, you don't know an awful lot of anatomy. The convention in CT imaging is that anything that is denser is shown whiter. So we have the bones here. These are the ribs. This is the vertebra. There's a bit of shoulder blade here and over here. This is the sternum. And that's how we can do a slice. But nowadays we can also do some much more sophisticated volume rendering, and you can see that over here. And what's been done here is that with sophisticated IT, you can cut away certain things. We've left, you see in this one, the ribs have been cut away at the front so we can have a good look at the heart area. We've got the kidneys here. You can choose what you want to look at. So it's a very powerful, very important method of doing X-ray imaging these days. So that's all I have time to say about X-rays. Let me go on and talk about ultrasound. Now, X-rays use the attenuation, the reduction in intensity of the X-rays as they pass through the patient. Ultrasound is different. What it does is it looks at reflection of ultrasound, rather like a radar system. It looks at the reflection of ultrasound from different boundaries. So this is an example of a nice rectangular patient. And we put some ultrasound in here, usually in the megahertz range. And this goes through the tissue, and some of it is reflected at a boundary between one kind of tissue and another. Some goes on, is reflected again. And what we need to do is to send in pulses and detect how long it is before they come back and how intense they are. And then we can build up an image, because this transducer here, which is producing the ultrasound, is also detecting it. It's a piezoelectric transducer. So lots of lovely sound physics in there. And let me show you a few equations that you can use in this. You all know these equations. This equation, I'm sure, speed equals frequency times wavelength, very important one. Another one, distance equals speed times time. This is school physics, and you need that because you need to work out how far the pulse has gone before it came back, and therefore where the boundary is. Then we also have an equation you might not be quite so familiar with, which is the amount of reflected sound as an interface between two tissues. Z is a quantity called the acoustic impedance, and is simply the density times the speed of sound in the medium. So if we have a big difference in Z, we get a lot of reflection. If we have a smaller difference, we get a smaller reflection. One of the consequences of this is that if we're dealing with an air or gas, air and gas have a very low density and usually a lower speed of sound. So we get a very low acoustic impedance in a gas. And that means that there'll be a very big difference in this top term here. And so you'll get a huge amount of reflection. And that means that ultrasound is not very good for looking at anything involving gas like lungs, because most of the sound is reflected as soon as it hits any gas. But it is extremely useful for looking at soft tissue. It's a very powerful and very useful, fairly quick method of doing imaging when you're talking about soft tissue. So it's used for all sorts of things. And I've got one example here, I think. Yes. Well, here's the transducer, which produces an array here, phased array here, sends out ultrasound pulses in different directions, all carefully timed, and measures how long it takes for them to come back again. And when we do that, we can build up an image. So the transducer would be up here, and the sound would be coming out this way in all different directions, and the time is measured coming back to the transducer. And you can see what this is. It's a fetus in utero, and ultrasound is widely used for that, but it also has an enormous number of other uses for soft tissues: kidneys, livers, hearts, prostates, ovaries, any soft tissue. It's very, 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 very useful for. Now, something else you might have come across in your studies of sound, in fact, I'm pretty sure you have as physicists, is the Doppler effect. And what we can do with the Doppler effect is we know that if we send a pulse of ultrasound in, megahertz ultrasound, and it's reflected off a moving corpuscle, then the frequency will be slightly changed by the Doppler effect because the blood corpuscle is moving. So that means that we've got a different frequency when it gets back to the transducer. Now, we can use that, and what we can do is we can make it that, the electronics can make it that blood moving in one direction is shown in red, and moving in the opposite direction is shown in blue. And we've got this as an example here. This is a carotid artery, a stenosis in the carotid artery, which is in your neck up here. And this is a bit of a mess, this carotid artery, because you can see there's all sorts of funny funny flow going on here. And this is an important thing to be able to diagnose. So we can superimpose the color on top of the B scan with the black and white B scan that we had before. Alternatively, we can do something a little bit more intuitive, perhaps, to us as physicists, and that is to plot a graph. And we can plot a graph of time and the speed. And this is obviously the heart beating here. So each time the heart beats, you get a fast speed, and then it slows down again. And you can tell a lot from the shape of this curve about that stenosis in the artery. And there is a third way also of using the Doppler effect, which is the convenient fact that if you work out from the Doppler equation what the change in frequency is going to be, it's actually going to be in the audio range. And so if you can make that into an audible signal, then you can actually hear the blood flowing. And if you do this, you can actually hear a whoosh, 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 whoosh as the blood goes through the artery. So that's very useful, particularly used by midwives with a little device that can listen to the fetal heartbeat. So another use of ultrasound, another use of physics. Moving on, radioactivity. Fascinating to using radioactivity in medicine, I always think. This is about imaging with radioactivity, which is perhaps not as widely known as things like X-rays and ultrasound. And this is how it works. What you do is you inject the patient, or some other way get into their body, a radioactive substance, which is designed to go into a particular organ which you want to image. And then you detect the radiation coming out of the patient, some sort of detector, more physics, and display a picture of it. And the great thing about this particular method of doing imaging is that it's an excellent functional imaging technique. It doesn't give you super duper images like the CT did, wonderful resolution and all that sort of thing, but it does give you information about the function of the organ. And that's really, really important. So it's widely used for that. Right, we're physicists. Let's ask some physics questions. We're going to do that process that we've just shown on the slide there. We're going to inject the patient, and we want to pick up the radiation, and we want to create an image. So, physics questions. What kind of emission are we going to use? Alpha, beta, gamma? What sort of half-life do we want? A few minutes? 1,000 years? Definitely not, because we're putting this into the patient, and we want to get an image, and the patient's got to go home afterwards. What energy of radiation is best? And now all of those mount up to the question, which radionuclide shall we use? And it's quite surprising how few suitable radionuclides there are when you look at all of those things, but lots of superphysics thinking to do there. We've also got to think about, once we've decided, what's the best way to detect this emitted radiation? And then there's other questions which you'd have to share with people like biochemists. How do you create a radiopharmaceutical that takes the radioactive isotope to the organ you want to image? Will it harm the patient? How can you reconstruct the image? And can you do 3D imaging? So all of these questions are here as for physicists to deal with and to work out the answers. So let's have a look at some images. Well, the first one I've got here is a simple whole body image. And this is a bone imaging system. Now you can see straight away that what I said before about the images being not terribly good resolution, it's absolutely true, but there's an awful lot of useful information in here. What's been done here is the patient's been injected with a radioisotope called technetium-99m, which is very commonly used in radioisotope imaging, which is linked to a phosphonate substance which goes to the bones. So you inject this in the patient and it goes to the bones. And what it will do after a few hours, it will accumulate in the regions of the bones where there is a lot of activity going on, a lot of metabolic activity. And that's what happens, unfortunately, if you have metastases from a cancer elsewhere in the body, breast or prostate or something. You often get bone metastases, and this is a very good way of diagnosing whether a patient has got bone metastases. Because what will happen is that where there are bone metastases, you'll see these dark spots where there's a large accumulation of the radioactive substance. Going on to looking at more 3D imaging, another very useful use of radionuclide imaging is in the heart. Now, if you want to know what about the blood flow in the arteries to the heart, this is not the blood going through the heart, this is the arteries that supply the heart muscle, and therefore are very important in keeping it going. Again, what you can do is you can inject a substance which goes to the heart muscle, and you can image the patient, and this is a 3D image because we've got a slice one way there through the heart and a slice another way there and another way there. And what we do with this one is shown in false color, and you can see that in some areas there is less of the radioactive material. And that means that in that area of the heart, there is not as good a blood flow in the arteries. And this is a very good indication as to whether or not the patient is suitable for a coronary bypass. I've even got, if I can get it to work, yes, I think I can. Yes, this is a 3D version, actually gated so that you can see the beating heart. It's the same idea as CT in terms of reconstructing the image. And what we have here is the heart seen from the bottom. And you can see here there's a region where there is not as much blood flow as there ought to be. And that is a very good indicator because a cardiologist will be able to say, I know which artery that is that's partially blocked, and we can do something about it. So it's a very important way of doing that imaging. And then there is a different way of doing radionuclide imaging, and that is to use positrons. Now, positrons are beta plus particles, if you like, beta plus emission. And a beta plus emitting material will emit a positron, antimatter. If you can put this beta plus emitter into the patient, to the organ you want to look at, as soon as the positron is emitted, what will happen is that it will collide with an electron, because there's an awful lot of those in our body. And as you probably know from your physics, when the two collide, you get annihilation radiation. We get two gamma rays in opposite directions at the same time. So what we can do is to set up a detector. Let's suppose our beta plus particle meets an electron here. We get gamma rays in that direction, then another one, we get gamma rays in that direction. And using the same sort of techniques as we use for the CT and the gamma imaging, we can identify where in the patient that emission has come from. And so we can build up a picture. Now, this is a more modern, more recent innovation. It's been around for a good few years now, but it's becoming more and more important all the time in hospitals. So there's a lot of very interesting work to do there. The problem with radionuclide imaging, as I've said, is that the images are not very good. They're rather blurry. They tell you, they've got the hot spots, but they're a bit blurry. So the best thing to do is actually to combine it with a CT scanner. And you won't be able to go out now and buy a PET scanner. You only will be able to go out and buy a combined PET CT scanner. And this is just to show you what happens here. The patient goes in here. You will have your PET detectors here. And then a bit further on, you will have the CT scanner. They're using different energies. The PET detector is using 511 keV, and the CT will be using lower energies, so they won't interfere with each other too much. The patient will go into both of those, and we get both images at the same time with the patient in the same position. So nothing's moved. They haven't had a drink or gone to the loo or anything like that. And so here we get the CT images, 3 different images. That's a coronal, a sagittal, and axial. And then we also get the PET images. There's 3 of those as well. And then put the 2 together. And what we can see very, very clearly is there's a hot spot there, which is indicative of the lung tumor. And that allows you to know very precisely where that lung tumor is. So if you want to do radiotherapy or surgery, you know exactly where you're going to go to get at the lung tumor. Now, magnetic resonance imaging, my time is probably already getting tight, so I'm not going to say very much about it. It is very complicated, magnetic resonance imaging, a wonderful method of imaging, again, developed in the sort of 70s and 80s. Very, very important nowadays, but I really can't say more than a few brief words about it. It's based on nuclear magnetic resonance, which you've probably come across in your studies. But on top of that, as well as measuring the signal, there's the extra problem of trying to measure where in the body the signal has come from. And that was worth a Nobel Prize for Lauterbur. He produced a paper which I always think is an amazingly short paper in Nature, which actually showed how he was going to do this spatial localization. In medical imaging, we usually use, almost always use, just the hydrogen nuclei, which you can do NMR with. And there's lots of them in the body, so we can use the hydrogen nuclei. What do we do? Well, we lie the patient in a very high magnetic field, several Tesla, which is a large field. The field's in this direction. It's a static field. It needs to be extremely homogeneous in space and time. And so for most scanners, we do this by, well, all these high field scanners, a superconducting coil, and you need liquid helium to keep the superconductor cool. So it's technologically complex. So there's the patient lying in the field. Now, when the patient is not in a field, the hydrogen nuclei, the spins of the hydrogen nuclei will be randomly aligned. Once you put the patient in the field, the spins will be aligned either with or against the field. Then what we do is we apply a radio frequency pulse, and we flip the spins. If I can try and sort of do this with my hands, if that's your spin direction, we apply a pulse and the spin is flipped. So it's now rotating in this plane. And when you do that, you can pick up a magnetization component in that plane perpendicular to the main field. Now, the interesting thing is that once that's happened, what happens, this is done best with a pen actually, what happens is that it's flipped, the spin is flipped, but it gradually goes back up to where it was. Now, the key thing is that the relaxation time for this to happen is different for different tissues. It's the same with X-rays. X-rays won't work unless there is a difference in the attenuation in different tissues. MRI doesn't work unless you have got a difference between different tissues. And that's the great thing that makes MRI so important. There are actually two relaxation times, T1 and T2, and they're different for different tissues. And that's what makes it possible to get useful images. Very complex sequences of fields that require you to know where the signal is coming from and how to flip the spins. But I'll just show you an image here. This is an image of the spine, and you can see that this person's got some problems with the discs down here. And you can see how well the MRI shows up soft tissue. This is much better than CT for things like this, much better. It's an extremely good method for joints, tendons, that sort of thing. These two images, one of them is looking at what we call T1 relaxation time, and one is T2. And the T2 tends to show up water brighter, which it's done here. But it's really excellent for imaging soft tissue. There's another MRI technique which is not so widely used in actually diagnosis, but it's very important in research. And that's something called functional MRI or fMRI. You may come across this. Fascinating this, what it does is it looks at the blood flow in the brain, and a particular type of sequence can pick up the blood flow in the brain. And so if you lie a patient in the scanner and you ask them to listen to music, think about mathematics, whatever it is, what you can then do is see which parts of their brain are actually working in doing that. So it's a fantastic tool for neuroscientists. So lots and lots of very interesting work to do there. On the diagnosis side, a couple of other quick ones that I want to mention, which is endoscopy. Very simple total internal reflection of light. So you've got your optic fiber, the same as we use for transmission of this signal between you and me, I'm sure. And there's the light will be reflected in the tube. So you can put the tube down the patient. You can put the tube in any orifice you like to think of into the patient. And it is done in a lot of different orifices. And then you can actually see what's going on. So this is an image here of what you might see going down into the patient's stomach. So a very important investigative technique. You can even also put an ultrasound, a tiny ultrasound probe down there, and do ultrasound on other nearby organs when you're down there. So that's another important bit of physics. And also this simple little device, which you may or may not have come across. If you've ever have an accident or go to hospital, quite very often what happens is somebody will slap one of these on your finger. And what it is a pulse oximeter. It works on the fact that the absorption of two different wavelengths of light, red and infrared light, is different. And so what you can do by looking at the proportion of those two wavelengths which get through the finger, you can actually work out how much oxygenation is in the blood. So this little device will come up here with a reading saying you've got 98% oxygenation, which is good. It will also at the same time come up with a pulse. But it's all based on some very simple physics, just simply on the absorption of infrared and red light. So I think I've got a little time to say a bit about treatment now. Radiotherapy. Well, killing tumor cells with radiation is actually pretty easy. The difficult bit is not damaging the other tissues around the tumor, and that's what makes radiotherapy such a fascinating challenge. It's a very successful way of treating many cancers, often I think are rather overlooked. We certainly in the UK, you read a lot in the press about chemotherapy and so on, but very little about radiotherapy. It's actually an extremely successful way, used all the time in treating many cancers. And a lot of physicists are involved in radiotherapy. 3 ways of doing radiotherapy. You can do it using external beams. Now those can be X-rays, that's the major one, electrons, or more recently charged particles. Then we can do brachytherapy, putting the source close to the tumor, or even unsealed source therapy, where you give the patient a drink or a tablet or something, a little bit similar to the idea of radionuclide imaging. It goes to the organ that you want to treat. So let's have a quick look at some of those. If you are interested in accelerators, this is the world for you. The linear accelerator, what happens here is that we have an electron gun. We accelerate electrons up this tube here. Being electrons being charged, we can bend them with a magnet. So we bend them round, zap them onto a target here, which will produce X-rays. Now these are much higher energy X-rays than we would use for imaging. This is all to do with the reasons to do with the interactions with tissue. But these are much higher energy X-rays. We're talking mega electron volts here. And then the X-ray beam will come down on the patient here. And this is what the assembly actually usually looks like. Patient will lie here. This is your linear accelerator, is up in here. And this whole assembly, the whole of this thing, will rotate around the patient, so that you can put the tumor at the center of rotation and rotate around the patient. And you need to do some very careful treatment planning, to try and make sure that most of the radiation goes to the tumor and as little as possible elsewhere. So these are the sort of treatment plans you might see on a computerized treatment planning system, showing you the dose going to where you want it and lower dose going elsewhere. So a lot of accurate calculations there, including Monte Carlo calculations, are behind these computerized systems nowadays for doing treatment planning. But it's a very important role in medical physics doing treatment planning. I mentioned also that you can use charged particles, and the most commonly used one is the proton. Now, if you are using if you're using X-rays, high energy X-rays, if we plot the dose against the depth, we find that actually the maximum dose is not terribly far. So that makes it a little bit difficult, and it means that there is some damage to tissues around the tumor. If you look at protons, if you look at a proton 150 MeV proton beam, what actually happens is that the protons all go along and then they suddenly dump their energy. It's known as the Bragg peak. They suddenly dump their energy over a much smaller distance. And if we can do that perhaps with several different energies, we can get something called a spread out Bragg peak. And let's say our tumor's from there to there, and we can dump a lot of energy in the tumor, very little energy behind it. So this is becoming very popular, particularly used in pediatric cases, where you want to try and reduce the dose to the rest of the body as much as possible. So you may well hear of proton therapy. There are not many installations around the world, but it is becoming more and more popular, proton therapy. We've just got 2 high energy ones coming on in the UK. Brachytherapy, as I said, involves putting the actual source of radioactivity close into the tumor. Now that always seems to me like a jolly good idea. So this is an example here of where you put little beads into the prostate, and you can see from this X-ray image here that they checked afterwards that the beads have gone where they want to go, and they can work out what the dose is going to be. So you usually put them in surgery, in theatre, and leave them there. A very successful method of treating, for example, prostate, but it can be used in other areas of the body as well. Alternatively, you can use an applicator which you put into the patient in theatre. This is a vaginal applicator, and then if you can just see the colours here, I don't know if you can see those. These are little beads of radioactive substance, usually an iridium isotope, which are blown in by compressed air from outside the room, so that nobody else has to be in the room and get the radiation. And they're blown in, held there for a certain length of time, and then taken out again. You can do that in the uterus and also in the lungs. Very briefly, unsealed source radiotherapy. This is a very similar idea, as I said, to radionuclide imaging. And what you do is you put in radionuclides, which produce short-range emissions, and they go to the tumor. Now, the most widely used one is iodine-131 for thyroid cancer. Very effective, very, very effective indeed. And the patient just has a drink, and they're usually shut in a room for a few days because they're pretty radioactive, and it goes to Calcium and samarium are also used for palliation of pain in bone metastases. And more interestingly, I think radium alpha emitter is now being used as well. So lots of interesting work to be done on that. And radioimmunotherapy using monoclonal antibodies. So loads of scope there for some very interesting work. Now, it's about time for me to finish, but there is one more thing I must mention. It is last but definitely not least, and that is the role of physicists in radiation protection. It is very important. We're using radiation. We've got X-rays, we've got CT, we've got radionuclide imaging, we've got radiotherapy. It is very important, first of all, that we protect the patients as much as possible. Any exposure of a patient to radiotherapy must be justified, which is a legal term, which means that it must be the diagnostic or therapeutic benefit must be justified. So it's very important that physicists are there to understand exactly what's getting what dose. And then, of course, we've also got to protect the staff and the visitors and make sure that the dose of radiation everywhere else in the hospital is as low as possible. So it's a very important role, and there's also handling radioactive sources. So that radiation protection is a very important role for physicists that should not be neglected. So there's lots more I could talk about, but I hope I've given you some idea of what an exciting field medical physics is. I'm sure you're going to hear more about it during the rest of the week, and I'm sure you'll enjoy it. But I hope I've given you some idea. And as Dan has already said, you can have a very rewarding career at the same time helping other people. So all it remains for me to do is to wish you good luck in your careers, especially if you go into medical physics. And I hope you have a very enjoyable and a very worthwhile time. Thank you.
Thank you very much, Dr. Liz, for that interesting lecture. We have a couple of questions for you, but we can't take everything now because of the time. So we'll take them after Professor Clark's lecture. So we'll probably just take 1 or 2 questions. So somebody asked the question that after imaging is done, what happens to the radioactive material injected in the patient. So I guess it's speaking of nuclear medicine.
Yeah, this is in radionuclide imaging. Yes, a very good question. The radionuclide that is most commonly used, but not exclusively, is technetium 99M, which has a 6-hour half-life, physical half-life, possibly a shorter biological, a shorter overall effective half-life, because you actually get rid of it too. So the effective half-life is a bit shorter. So you have injected but once you've injected the patient, you've got to often wait a few hours before you can actually do the imaging, for example, in the bone one. So you have to have a special patient's waiting room. So anyway, the main way that the patients will then get rid of the radioactive material is by excreting it. So in a nuclear physics, nuclear medicine department, you have to have a special patient's loo. And the patients go to the loo in there. The half-life is only 6 hours, so it is generally reckoned that by the time it's got through to the sewage system, it isn't going to be a problem anymore. So that's the answer really to how you get rid of it. You do have to advise the patients. Particularly, I'm perhaps thinking more here about the brachytherapy patients who've actually had seeds put in them. What they can do, for example, gentlemen who've had prostate seeds are advised not to sort of have their grandchildren sitting on their knee for a while, because they will be slightly radioactive. So yes, there is advice given to everybody who's had anything like this. And in fact, if you're going to go and fly on an aeroplane, you need to have a certificate, because they actually pick up radioactivity coming out of patients. I never realized this until I heard about it, that when you go through into an airport, they're actually, as well as detecting metal, they're detecting radioactivity. So I hope that answers the question. It's dealt with by
Thank you very much. Yes. So another quick one. What sort of processing do we apply on the images? So this person is trying to find out how we process X-ray images.
What sort of, sorry, processing? Is that what you said?
Processing, yes.
Yes. Right. Well, with digital imaging,
the question, okay.
Sorry, I think with digital imaging, you can do all sorts of great things, because you can use image processing software. I don't know if you've ever used anything like ImageJ, which is a very good image processing software. You've possibly used it on your photographs these days. You can play around with your photographs and change the contrast and so on. But with looking at things like CT images and X-ray images, you can do a lot of post-processing after the patient's gone. You can actually have these images up on screen, and you can do that sort of thing. You can enhance the edges, you can change the contrast, you can window it and things like that. So yes, there's lots you can do to it. Does that answer the question?
Yes, I think so.